In MCQ 18, this is a question with regards to transition metals, and we need to find a pairing of the complex with a correct description of its physical state. Now this is a rather quick and easy question. So to look at the term precipitate for most of your complexes, there must actually be the presence of hydroxide in the formula itself. So if you do have hydroxide, you are a precipitate, and without that, you are not a precipitate. Now for the case for B, this is wrong. You can see that in the formula of the cation of a hexaamine copper 2+ cation, there is the absence of hydroxide, and therefore it should not have been a precipitate. But for the case of C, you do have hydroxide, but yet the term solution is used instead. So both B and C is actually eliminated. Now we're left with A and D, and both suggested that it was a solution. So now, if both are solution, if you look through the formula, there's also the absence of hydroxide for both A and D. So I'll still say that they are still along the right track here. Without hydroxide, they can still be a solution. So if solution or the state of the metal is not for comparison, the next one here would have been to talk about the color of choice over here. And one of them is actually that of dark blue, and the other is that of a pale blue. So let's take a look at the formula of the cation, as also to find out the oxidation state of copper within. Now for the first case here of a tetraamine diaquo complex, you have a 2+ charge here, meaning that copper has a charge of +2, since per ammonia and per water is actually 0. Now repeating the same thing for option D, this is a hexa-aquo copper complex. Water has an oxidation state of 0, and since the overall charge here is plus, copper must have an oxidation state of +1. So I have a Cu+ and a Cu2+. Now writing out the ground state copper electronic configuration of 29, you have it as argon that holds 18 electrons configuration, a 4s2 and a 3d9. Now it's important to understand that apart from copper, chromium as well has the same observation, whereby one of the electrons from the 4s subshell is actually transferred towards the 3d subshell, so that it can form a more favorable completely filled 3d10 orbit and a 4s1 configuration. Now I did mention that for chromium, that comes on with a total of 24 electrons. Initially, it has a configuration of argon, 4s2, 3d4. So again, one of the electrons will move down from the 4s, so that chromium can actually have a more favorable configuration of 4s1, 3d5, which is a half-filled orbital. And in the case of copper, this becomes a fully filled 3d orbital. So for copper 2+, I'll be losing 2 electrons from the furthest shell. I will have an argon, 3d9, 4s0. And I have a partially filled 3d subshell. And with this partially filled 3d subshell, I'm capable of going through ground state D to excited state D transition. Now it's this transition that gives the color off, because during this transition itself, there will be a certain wavelength of light that is taken in, and with response to that, this will actually result in a complementary wavelength of color of that light to have been released. Now this could have been visualized by the color wheel itself: red, orange, yellow, green, blue, and violet. Whereby in this case here, red and green are complementary colors, yellow and violet are complementary colors, and orange and blue are complementary color. So for example, if let's say we are to take in red light, the complementary of that, it will have been green light that has been seen as the color of the complex. But if you take a look for that of your Cu+, the configuration is actually argon 3d10. And in this case here, this is a fully filled 3d subshell. And it being a fully filled 3D subshell means that there is actually no d excited transition, and this compound itself, this complex itself, should have been colorless instead, without any color, because no light is taken in and no complementary is actually given out. So D is incorrect and A is the correct answer for this question.